Okay, so the last two seminars we covered Q learning and deep Q learning. And a quick recap on that is in Q learning, what we're basically doing is we are trying to estimate the expected return that you're going to get for each action, right? So it can be thought of creating a table. Right? And for each state, we're going to try to estimate the expected future return for each action. So this could be 2, this could be 0, this could be 0.5, could be 7, etc. And based on that, when we wanted to exploit, we would choose the best action available. Okay, and when we wanted to explore, we would have to use some kind of strategies like greedy epsilon, or we also tried using a decayed epsilon. So some kind of strategy we'd have to implement separately to explore, right? Now, when we come to policy gradients, firstly, what is a policy? A policy is basically given a state, right? Okay, so given a state at time t, we want to determine what action to take at that time t. So it's basically a probability distribution. Okay? Fine? So it's a probability distribution of actions given a state. Right? Now, in policy gradients, what we're going to do is we're not going to create a table or anything like that. We're basically going to learn this probability distribution. Okay? And our network is going to basically take in your observation, right, and return a probability distribution for the actions. Okay. Now
I have a question for.
Right.
So, in the Q learning,
right,
the numbers are like a reward, right?
Right.
So, in the policy.
Oh, sorry, wrong room.
Yeah.
Yeah, we're good.
So, in the policy, it's a probability distribution of action given state, right?
Right.
So, if I am ideal, right, I will probably choose only the maximum reward action.
Right.
Then the probability distribution will be only the maximum reward action. Or if the reward is distributed, should I do proportionally to the reward, or what?
So basically how it works is we're going to try and use the expected values to update this probability distribution. So given a trajectory, right, so that means from your start state until your end state, if you get positive rewards, you're going to basically increase taking the actions that you took. You're going to increase the probability of taking those actions, right? And if they're bad actions or very low reward compared to other actions, you're going to decrease the probability, right? So in that case, you create your probability distribution so it takes care of exploration as well as exploitation.
Okay, so if after enough learning,
Yeah.
should the probability distribution looks very similar to the reward distribution?
Ideally, yes, but when you think about it here, you're always taking the best action, right? You're never taking these actions. You're only taking these actions when you're exploring using greedy epsilon. So there may be
So we build a very focused on the best action, right?
Right.
Okay, I see. Thank you.
So now when we come to this, we basically need to have some kind of objective function, right? Or like a loss, but in this case it's a score, right? Because we're trying to maximize the score. So in our case, our objective function is the expected value given a policy for the rewards for the whole trajectory. Okay, this symbol is for a trajectory. That means from your start state until your end state, all the action states rewards that you get, right? Okay, and we want to basically maximize this expected return. And then what we're going to do is we would basically update our weights using the normal formula. So at t plus 1 is equal to at t plus alpha into the gradient of your scope function. Okay. Now basically we need to learn how to calculate this gradient. Okay. So this is a expected value. So you can, this is not a very hard derivation, but let's go through it. So an expected value is basically the probability of being on a trajectory. So p of x into x, right, into the reward for that trajectory, right?
I have a question.
Yeah.
What do you mean by the trajectory?
So the trajectory basically means all the sequences from your start state to your end state.
Mm-hmm.
Okay.
Mm-hmm.
Right. So now we want to take the derivative of this. Okay, I'm just going to take it inside so that we skip one step. Okay, and we're going to use this identity, and basically we're going to use, it's called the log probability trick. So basically the log of a derivative, let's say log of f of x is equal to 1 upon f of x derivative of f of x, right? So if I rephrase that, derivative of f of x can be written as f of x into the gradient of, right?
Mm-hmm.
So we're going to substitute that here. So we get, in this case, okay, and if you look at this, this is still an expected value. This is the probability of being of a trajectory, and in this case, this is your x, right? So we have basically reformulated the problem.
Oh, what is that? The logo pi x.
So you can take this as
Hmm.
this part as your probability of x,
Okay.
and this part as x. This is a function, right?
Oh, I didn't get it.
So for an expected value,
Mm-hmm.
an expected value, so expected value of f of x is equal to the integral of the probability of x into the function of x, right?
Yes.
So in this case, this is still your probability of being on a trajectory,
Mm-hmm.
and this is your f of x.
Okay.
So we've reformulated into a different expected value,
Mm-hmm.
right? So this is now into the reward for the trajectory. Okay,
Mhm.
and this equation is the policy gradient theorem, which basically states the derivative of the expected reward is the expectation of the product of the reward and the gradient of the log probability of the policy.
Can you write it down?
Yeah, I'll write it down. So
Okay.
Now, all we need to see is what is actually there in this term. Okay? So, first let's consider just the trajectory, right? So this trajectory, so the probability of being on this trajectory is basically first the probability of the start state, okay, into the product of the probabilities. So t is equal to 1 to t, right? So the product of taking an action at each time step over the whole trajectory into the product of given state t and action t, right? So what this means is there are certain environments that are not deterministic, in the sense that if you take an example of windy grid world, basically you could move 4 directions, but if you take a step forward, since there is wind, there's a chance that you may not actually move forward, right? So this, if it was deterministic, so if you always move forward and there's no wind, it would be 1. But because of the mechanics of the environment, it's not necessary that you move to the next state. So this is the probability of getting the next state and the next reward given your state t and action t, right? So if you see, this part and this part require knowing the distribution of the environment, right? So now we're going to see how that will not matter. Okay, so what we're first going to do is take the log of this. And let me just put this here, because this policy depends on your weights. So log of p is of s0 plus, because it's log of a into b is log of a plus b. So now this becomes a summation. And let me just put a bracket here so this makes more sense. Okay. Plus okay, and now we're going to take the derivative of this. This becomes 0 because it doesn't depend on theta. So this is 0. And this as well becomes 0, right? So basically we've reached a point where we do not need to know the mechanics of the environment to calculate that derivative.
Derivative with respect to what?
Theta.
Okay.
Okay, and this is what's called model free environments. Okay,
What do you mean by model free?
they don't, so how you have the world model, you're trying to model your environment. Here you're not trying to model the environment,
Okay.
the mechanics of the environment basically.
Mm-hmm.
Okay, and that's it. So all you need to do now is plug that into this formula. So you will get the derivative of your scope function is going to be the expected value of into the reward. Sorry, just the reward. Okay. And this is
Let's just remove it to make it correct. Yeah.
which,
In the expectation.
oh.
Yeah.
And this is still an expected value. So in order to optimize this, you have to take a large number of samples. Okay, so and that's why these algorithms take a lot of time.
Can you explain how taking large number of samples in a concrete example? So how we can get an expected value of that number from?
So
Let's put a simple game. Which game do you want?
we are going to use card poll, but actually that may not be the best example because it finishes quite quickly in 300 examples. But let me think. So let's take the multi-arm bandit problem.
Multi-arm bandit?
Yeah.
Okay.
So basically, in that game, you're trying to estimate the mean of the number of times that you're going to win, right? And say you have 3 slot machines. Okay, you have the trigger. Okay. Taking just say 5 examples from this machine, and suppose you happen to win in those 5 examples, you may have a very high estimate of your estimated expected mean value, right? And you may think that that's better than these two who in the first 5 examples you may have lost, right? But using just that low number of samples, it's not an accurate enough estimate, so you cannot keep exploiting this.
Oh no, my question is, let's say we are doing multi-arm bandit, and so the process is first randomly select or given a random policy, according to the policy select the which bandit,
Right.
and then do the experiment and then get the reward, and
Yeah.
we just add all those reward to get the expected value of this policy, right?
Right.
Okay.
So say in this example, your expected reward from this is in the first 5 is 10, and this is only 5, right?
Yeah. So given state T, action T. In this case, there is only one state. Or can you do the manually those equation? What will be the sigma T from 1 to T policy action T given state T?
Let me think. Okay, it's a very rough example because it's difficult to write this down. But say this is your probability distribution on which bandit you want to exploit, right? So suppose in the first 5 examples, your reward is here is 10. Suppose these two are 0. Okay, let's say this was 5 and this was 0. So you have a probability of exploiting this could be 2/3. Probability of exploiting this could be 1/3, and with the initial estimate, your probability of exploiting this could be 0. Right? Now, when you take more examples, these figures will change, and you suppose in the next 5 examples, this expected reward may reduce. So say it becomes, this one becomes 5, right? So it changes to 5. You want to reduce this probability. and say this one increases to 10, you basically want to increase this probability,
Okay.
right?
Mm-hmm. Okay.
So any questions? Okay, then let's go to the code.
Can you give me, in a high level, what is the benefit and advantage and disadvantage compared to Q running?
So one major advantage of this is, so in Q learning, suppose you have an action that is continuous.
Mm-hmm.
Okay, so say it could take from minus infinity to infinity.
Mm-hmm.
Okay,
Mm-hmm.
then to estimate at every point, each possible point is impossible, right? It will take way too long.
Mm-hmm.
Okay, so you could use policy gradients to directly output a probability distribution, one probability distribution, and then sample from that.
Oh, I see.
Okay, and but one drawback of policy gradients is that
Can you explain again what is the?
so in Q learning, suppose your actions could take the values from minus infinity to infinity. It's on a continuous scale, right? So then when you need to estimate at every point which action is best, you basically need to assign scores to like a infinite number of points. Okay? Whereas in policy gradients, you have one probability distribution and then you sample from that distribution. Okay?
Can you remind me what is the benefit of using deep QN?
Deep QN is basically
When the state
you
is
have a function approximator. Yeah, so exactly. So if the states become infinite,
continuous.
yeah, continuous or even right, continuous.
Mm-hmm.
You use a function approximator to approximate the state that gives you a set of values. So the states could be similar,
Mm-hmm.
and it would the network would decide how to return the values.
Okay, so we have a Q. What is the Q running? Q
Yeah.
running, and when the state is continuous or infinite, then we use the DQ network. When the actions are continuous, then we use a policy gradient.
Right. And there are other advantages as well. I think
Mhm.
policy gradients they converge faster,
Mhm.
but I think they're susceptible to like local maxima. And then there are other ways to deal with that when we go to A to C and things like that.
Okay. Is there any relationship with the policy gradient when the state is continuous or infinite?
It's the same thing. It's a
Is it-
neural network, right? So you can.
So we can use a neural network
Right.
on the policy gradient.
Yeah.
Okay. Okay.
Okay. Okay, so we have our imports. So we need gem, numpy, and TensorFlow. Then we're going to make our environment. We're going to get the state size and action size. So this is a box 2D game, so you need to use the shape 0 to get the state size. Okay, let's just print that. Okay. So there are basically four. In each state is a vector. The state representation is a vector having four values, and you have two actions going left or right. Okay. We're gonna just set some parameters. Max episodes is 300 and turning rate is equal to 0.01. Gamma is equal to 0.95. Okay, and then we're going to create a function called discount and normalize rewards. I'm going to use an abbreviation just so that we don't have to write this. So this means discounted episode rewards.
So in cut 4 is a continuous environment, right? Or
The states are continuous. In this case, the action is still discrete because I've taken a very simple example.
okay.
Okay, and so this is similar to what we did earlier. And one more thing I wanted to point out is that we're not doing TD learning right now. We're using Monte Carlo, which is basically going to finish a whole episode, calculate because we're not estimating the future reward, we're taking the actual reward that it got in that trajectory, and so we're going to reverse the loop, calculate the cumulative, the discounted reward, and use that. Okay.
Okay. Paul, I'm sorry, but can you remind me the temporal difference and Monte Carlo? I remember hearing the lecture at our first.
Yeah.
Yeah.
So in temporal difference, basically, say you have 10 steps, okay? And especially when we were doing Q learning, what we were doing is we were not using the actual future reward that we got during that learning. We were basically using so basically what we did was at step 1, okay, we got Q of S1 comma A1, right? So this was the current value, and then what we were doing is
What's the QS1A1? Is it reward?
the expected reward from the table that we've learned,
Okay.
right?
Okay.
And then what we did was we took the best one, max of that, took the best one, and we applied it to the environment. So we did environment.step using that action, and we got a new state over here, right? So we got S2, right? And then what we were doing, we were taking S2 and using it here, right? And that was the estimated Q value for the next state, right? So we were using that to train the algorithm. Whereas in Monte Carlo, what we're doing over here, so basically we could do this at every step. We didn't have to wait for the end. In Monte Carlo, what we're doing is we're waiting for all steps 1, 2 up till 10, and then you are going to backtrack and calculate the actual discounted value. So if at step 10 you got 1, right, your expected value here will be 1. If here you got 1, so each of these you got 1, here you'll multiply it by gamma, so 0.95 into 1 plus the current reward, which is 1. So it'll be 1.95. Here it will be 1.95 into 0.95 plus 1. So it will keep going back like that. Okay?
Okay. So during that up to 10 sequence, we are following the policy.
Right.
Yeah.
The current policy that
Yeah, okay.
we have. Okay, so reversed range. Okay, and we're going to normalize it.
What is the DEI? Is it?
Discounted episode rewards.
Okay. What is the shape of the episode reward?
This will be every time. So in each episode,
Mm-hmm.
it depends on how long you last. So if you last for only 10 steps, it will be a vector of 10, 1.
Okay.
For I in. Okay. For I in reversed.
Mm-hmm.
Okay, now we're going to build our model. So we have a placeholder. Okay, so we have a fully connected layer. Your inputs is going to be your inputs. Your activation function is going to be relu. And second layer is going to be again 10 nodes.
much number of outputs is 10?
It's your hidden size, it could be anything. It's a parameter, hyperparameter. But in your last layer, in this case, you're gonna have your actions. So we're going to need the probability distribution. So here we're just going to use a simple softmax with FC3 as the input. And we basically need to return this so that we can sample from that distribution. There's a typo over here. There's a typo over here, so just check.
Yeah.
I just corrected. Xavier initializer and FC3. All done?
No.
What is softmax cross entropy with logis?
This will basically calculate the log probability between your logits. Here is FC3, which is what you've just generated, and your labels are the actions, which is all the action that you took.
So, what is the FC3, so FC3 generates size 10, right?
No, it will generate the action size.
No. Okay, yeah, action size. So what is the action size?
In this case, 2.
Okay. So it will generate a 2 output. It
Right.
will be probability for each action, left,
Right. And your labels is the actual action that you took
Mm-hmm.
while playing the episode. So it's going to be an input to the network.
Okay. So that is calculating in our formula. What is this one is calculating?
This one is calculating the if I'm not wrong, it is this. The negative log property. And let me just open this.
DER. Yeah. So loss is basically the entire term expected over policy.
Right. Yeah.
Yeah. So because we are using negative log probability, we want to minimize the loss, which is basically maximizing the expected value.
So this is a good example actually. Basically, you will get the softmax values, and in this case, since we're taking a very simple example, we'll have a one-hot encoding of 5 actions, and it will calculate it only for the action that you took.
Okay.
Right? Now we do cross entropy, the zeros get removed, and then you'll get your result like that.
Can you go DE?
When do you use action distribution?
I'll show you in the loop. So basically, whenever you're generating your rewards, you'll call this network only to get the distribution. You'll get the distribution, you'll take a sample of it, you'll go to your environment, get the reward,
Okay.
and then at the end of the episode, you'll call the network again to update the base. Can we go ahead? Okay, so right here. right? In this case, it's 300 episodes. So we're just gonna create some lists. So episode states. So at the start of each episode, you're gonna reset your environment, and then, like normal, we're gonna do while not done. Action probability distribution. So you're gonna run the session, and in this case, you want to get your action distribution, and you're gonna feed it in this case your inputs is gonna be just that one state, but you're gonna have to reshape it. In this case it's your, what is it, state size, right? You're gonna reshape it because it's expecting a batch of inputs.
Expecting what?
A batch,
Okay.
right? So what we're gonna do now is we're basically gonna sample from the distribution. So your range is gonna be action.
Is this a stage or state? There is a
Right.
stage and
Yeah.
no, input equals a state dot reshape.
Oh, sorry. There should just be states.
Mm-hmm.
Okay, and you basically want to give it your probabilities. So you say P is equal to so dot travel is going to make it one vector. So it's basically going to remove the extra dimension, because everything from the network is a batch. We're gonna make it 1 hour encoded, and then we're gonna append everything to the list that we have. See what we can do here is so at the end of updating. I mean, once you add it to the list, you can assign the new state to the current state. Okay, and then if it's done, basically you want to update your parameters. So let's just print episode number, comma, okay.
Paul, what does that one hot action equals to 1 does?
It's basically your action is in this case 0 and 1, because you have two actions, right? So if you have a one hot vector, right? So if you assign to this vector, so if this is equal to A, right? So if you do A for 0 is equal to 1, that will make this one 1. And if you do A not 1 equal to 1, this will remain 0 and this one will become 1. Okay.
So what is the size of action probability distribution? Or the shape?
Probability distribution, in this case the shape will be 1, 2.
Then what does Ravel do?
Ravel will basically make it a vector. So in this case 1, 2 is basically a vector of size 2, right? So it will remove the extra dimension.
So it will keep the later dimension 2 and
Yeah, it will remove this. It will create one vector. So basically, if I'm not wrong, if this was 2, 2, it will make this a vector of 4. I'm not sure about that, but you could confirm. Or you could just use a reshape function. Okay, so we need to get our rewards. I'll use an underscore here just so that it doesn't clash. Now we want to run the loss and the optimizer, and our feed dict in this case is going to be all three. So first inputs is going to just be actions. Sorry, what did we name this? DAR. This bracket should close here. Okay. Because we want the range to be one argument and your probabilities to be the second. So you need to close the bracket there and remove the extra bracket.
Okay.
One second. HDI. Standard normalized. Give me one sec. Okay, there's an issue with actions, episode actions. Yeah, so basically what I did was I appended the actual action instead of appending the one hot action, right? So you need to change that.
Can you go back to the code?
Okay, that's it.
Inputs, yeah.
Just correct this. Then you'll have to change this. I appended the action instead of the one hot encoding action.
Okay.
Zoom in on it too. Yeah. And down.
Do you have
return
any
pattern.
questions? Paul, can you help keep showing?
Any issues?
No, it's, so how much will the maximum reward?
Keep going down. Maximum reward is 200.
Can the convert method in
Yours is working.
method in action power has this
Fly in. Alteration of the
action
scope.
problem distribution method into tensor action distribution. Action distribution.
Outputs, yes.
So there was no.
Yeah, there is no bracket. Yeah.
Mean.
Why did that mean?
P dictionary 그냥
Well,
That was
before this.
I think it's inputs.
You didn't put equal to. Now you put equal to. Earlier equal to was random.
Inputs.
Or maybe you did not drop.
Okay.
Yeah.
So string object can MP0's action state. So this is not string.
No, it's
No,
not.
that's
Comma.
930.
Comma.
Episode rewards. Number 25 rewards you. Just a second.
Yes.
Yes. Yeah, rewards.
Like first.
This is underbar.
So what's the difference between underscore and regular one?
Underbar means this is a very
Yes.
temporary or you do not want to use this variable very you do not this is a very temporary variable temporary name you do not want
Actions.
use it widely, right? For example,
Uses.
these variables you use it everywhere, right? But this variable you do not want to use it everywhere. For example, if it's just underbar, you do not want to use it.
Zeros.
Yes.
Paul, can you explain why you put underbar here in the
Because we already created a variable in your main loop called der over here, right? You don't want that to clash. If you override that variable, this variable will get removed.
okay.
Cumulative over here before the for loop make it 0. Zero point zero. So
I see. Let's go to the definition of this function. So one quick touching method is
Where do we run DER underscore?
and run, and here
It's supposed to be DER underscore.
yeah, you have to run everything.
so
Cannot convert into 32
So what?
cannot interpret field it.
So on.
this code and normalize reward. So in first episode, there is a 1, 2, 3, 5. So for me there are 18,
Every line
but
is
because this is random, it does not matter.
It's
I think you are
inside the tensor. Here,
okay.
line 31. DRE.
Can you show me your function?
Yes.
This function normalize. Right. Can you run everything again?
Yeah.
Can you print out all the three values?
After
Can you print episode actions? Add the print here and replace it to the episode actions.
Here, right?
Try to make it numpy array episode action.
Episode input. States.
And compare it with my project. The reason why I'm saying is it might be DER on the bar. It can be any of these two, can be also error. Yeah, add the print.
You didn't run it. Last. Last.
it's not. They're all short.
Below, this is DER and the action is same. So, in my case, the name of the place.
So something is wrong because first you're printing this, you're printing
See,
this before
there are
you
name.
initialize it, and there's some, can you restart and run the whole thing? Would have gone.
Side by
You probably have to move that pen straight.
See inside here, if you have a DER on the bar elsewhere,
Okay, it prints action and then it fails.
or
No.
check the names.
So it's failing before that.
Yeah.
No, what you would have? You would have print
No, you told to move.
move it after the underscore.
Maybe because inside that function, but that doesn't matter.
Before the loss. Before this.
Inside this function, what you have defined, it shouldn't matter, right? DER or DN. Because it's just written.
Yeah, I think it's the inside function. I use the same DER.
Printed all the years and then it fails.
Can you show me on network?
Save use. It's 10.
You know what? Do you know what was the error?
The session was not right.
So you already overwrote the DER. So DER was defined here. When you run only one time in this shell, this was replaced already. And we were updating this and running only this cell.
Okay. So it's not getting the real DER value.
Yeah.
Thank you.
Shadek, are you
Yeah.
okay?
Not sure what's happening. Something to do with actions. You don't, can you, instead of printing this, can you print the actual values you're passing to the network, which is this?
Okay.
Okay.
So actually, loss function is coming from which formula? The loss is defined from negative log probability times DER.
Yeah.
It's coming from which?
The last expected value for the policy pi, the derivative of the log of the probability of the trajectory into the reward of the trajectory.
I think this one. It's a loss is minus of this one. So we want to maximize this one. So what's the error type?
Cannot, it says cannot convert into
And what is the interest in action?
actions. Right?
But the values are not in. I'm printing the values.
What is the action? This one? This is the, I think, the right action.
So it's 1 point.
Magnitude. And network definition. Here you use the actions. Right? This is the tensor placeholder name. Then you are using the name. So change the, go to the,
Here,
here.
actions.
Yeah.
That error.
And unknown word.
Yes.
Restart and go to kernel. Restart and
Okay, thank you, Paul. It was very good seminar. Everyone, please, thanks for the great seminar. And Sadek, we will have a meeting. Paul, let's have a quick meeting.